In the previous video, I introduced surface integrals, and we really kind of talked about three different surface integrals. The first was just the surface area. Second was a scalar function integrated over a surface. And these two kinds of surface integrals we're not going to talk about much beyond this. We had ways to evaluate them. And then the one we are going to talk about is the flux integral. And I talked about this in the previous video. Here's the statement, or here's the definition of the flux integral. This big F is a vector field. Here our surface is a two-dimensional creature in this three-dimensional vector field. This N is the unit vector normal to this surface. ds is the differential piece of surface area. We integrate this over the entire surface. So what's inside the integral is a differential piece of flux, and when you integrate it over the entire surface, you get the total flux. This is the flux integral. And we went through and said, here's a way to evaluate it. We have to parameterize things in terms of two parameters or two variables. We call them u and v. So the vector function is now converted to a function of u and v only. R, remember, was that position vector to the surface. We had to have it parameterized in u and v. R sub u is the partial of r with respect to u. This is the partial of r with respect to v. And dA is the differential area in the UV plane. And this R, the region of integration, is also in the UV plane. So let me go through an example of how to actually do this. And by the way, when we get an answer, the convention for what positive flux means will be, whoops. What happened there will be in the direction of this cross product. Whatever this cross product is, and it might be different at every point on the surface, that's what convention for positive flux means. So if you get a negative answer, it means it's in that opposite direction. So it doesn't matter if you do R cross V or RV cross U, as long as you understand what it means physically. So here's the example. Our vector field looks easy enough, 0, x, 0. The surface is a sphere of radius a, but only in this one octant, where all x, y, and z are positive. Well, step one is to parameterize. And we had a way to parameterize a sphere. Here was a way to parameterize a sphere. Now we're only in the positive x, positive y, so our u will only go from u to pi over 2 instead of all the way around 2 pi. And our v will go from 0 up to pi over 2 also. That's our R. This is now our surface parameterized in just two variables. Our vector field becomes this, x. This is the x part, and that's the y component of f. So we put that x there. Wherever there was an x in this f, we replace it with this. If there was a y in here, we'd replace it with this. Wherever there's a z in this f, we replace it with this. In this case, it's kind of easy. All we have is the x, and it just goes in one place. And here's the limits of those u and v. There's our parameterization. What do we do next? Well, I take these partials. Yep, let's take those partials. Here's what R is. Let's see, with respect to u, minus sign, everything else stays the same. By the way, everything has got this constant a in it, so we can pull it out front. With respect to u will be positive cosine. This with respect to u will just be 0. And this with respect to v will be minus sine v cosine u. Same thing, minus sine v cosine. Anyway, you can take partials, right? So that step was easy. What do we do now? We'll take this cross product. Well, we can pull an a out of both of them. So there'll be an a squared up front, and we'll set up our determinant notation for a cross product. This all harkens back to other subjects we've already covered. The cross product. So r sub u, this guy goes in that line, cross r sub v, there's our r sub v. Know how to take a cross product? I'm not going to go through this. The I term will be this guy times that minus that product. Anyway, go through that, and here's what you get. Here's that cross product. What do we got to do next? Take this dot product. We step forward, take the dot product. Here was our f. Here was our ru cross rv. So now we've got an a cubed because they all have an a in them. Do that dot product. I won't go through that. It simplifies a bit, and here's what we get. Finally, we have something we can integrate, right? All we need to do is integrate this stuff. And now we have the dot product. It is this. And dA was just du dv. And they both go from 0 to pi over 2. Here is the double integral we need to take. And at this point, it's just normal calculus. Normal take a double integral. This one breaks up as a product. Got a cosine cubed, and then this guy, cosine sine u. This guy would be easy enough because the derivative of, either way, the derivative of cosine is, well, the derivative of sine is cosine. So treat sine u like u. Anyway, this guy was tougher. I needed to look it up in the table. But this, everything past here is just normal calculus. So this is the part I would emphasize in my courses, my classes on my exams. Getting this right, including the limits. After that, it's just, can you take an integral? There's the answer. It looked easy, 1/3 a cubed. Do another example next time. Remember, there's going to be simpler methods we can employ in certain situations. We'll get to them later.